Hi, good morning. I'm audible.
Yeah.
Yes.
Okay, thank you. Um, so again, waiting for a little while, just letting everyone in, and then we'll start. Yeah, 1 more minute, perhaps. Yes. So all the recordings, they are initially saved to the cloud by Zoom, and it takes some time for the processing to get done at their end. But I try to download those recordings and put them up on YouTube because because the Zoom storage is limited. So I generally do that over the weekend. So all the recordings from the previous week, and there was only one because the first session could not be recorded, but the second session was indeed uploaded to YouTube, and I had shared the recordings. They are pinned in our private channel, which is private to this cohort, and the same will happen to Monday's recording. Right now they are on Zoom. I have shared the link in a thread on the general channel, but eventually by the end of the week I'll put it up on YouTube, and then today's recording as well. Okay, I think we're good to start. So on Friday and then Monday we were trying to finish our implementation of the foosball class that we wanted to implement as a test bench for everything we want to do with reinforcement learning. And I think by Monday everyone had finished sort of implementing the class, uh, and we essentially spent the entire session on Monday doing just that. So if there is still anyone who hasn't figured it out, it's not a big issue because the recording is there, and I'm also in a moment going to share the link to today's notebook, which has the full implementation, and we'll start from there. Before I do that, there was a question on Monday's office hours about debugging. So I showed a small demo, tiny demo of how to do it in Jupyter notebook, whether it's in Colab or you're working on your computer. You just need to use %pdb as a magic command. So just put %pdb at the beginning of the cell where you have the code that you want to debug, and then anytime there is an error, you will see that the debugger launches, and then there is a prompt where you can input commands to look at the stack trace and print variables and go up or down the stack trace. So you can do pretty much everything. uh, you can also convert the Jupyter notebook to a script if you want full-fledged debugging. So you could do the conversion and then debug it in Visual Studio Code or another IDE. Unfortunately, at this point, it doesn't seem feasible to do full-fledged debugging. If you just download the notebook and try to open it in Visual Studio Code, then your options are limited. So either you do the debugging in Jupyter notebook itself, or you convert it to a script, a Python script, and debug the script. And most of the time, I think most of the issues can be just debugged by using printf carefully, which will see perhaps in today's session. So to start off, I'm going to share my screen. Okay, so there's a message about. Could you share your email, please? If someone is not added to the Slack channel, please DM me your email address, preferably your Qualcomm address. Okay, is my screen visible? Can you see my screen? Please confirm.
Yeah.
All right. So this is where we sort of left the implementation on Thursday. So first of all, you need to open this notebook, which is again, I'm going to ping the entire path, but it is there in the course repository. I just pinged it in the chat, but you can also go to the course repository and browse for the folder for this week, which is W2S1, and inside you have foosball.ipynb, and that notebook has to be opened in Collab. So while everyone is doing that, there's nothing new. These are the same definitions. So I'm just going to run these two cells. There is one minor bug fix that I'll show everyone, but if you're pulling the code from the repository from the link that I just shared, this bug fix is already included. If you want to continue with your code with the notebook that where you implemented the code last time, that is also fine. But in that case, just make sure you apply this bug fix, which I'm going to show in a moment. So these were the initial definitions, and then this is the entire class, and there was a small change right here. Yep. So on line 99 to 103, so there was a condition which tested if the next state is valid or not, and there were two conditions. We were basically checking if the row and column, if they are within the bounds of the field. But I also realized that it could be that you are in a terminal state and then you are trying to carry out an action in a terminal state, in which case the next state is again going to be invalid, sort of, because you can't make a transition out of a terminal state. So I have added this condition right here, this line 102. If you don't have in your code, you need to include this manually. If you're pulling the code from GitHub, it's fine, but the rest of the code remains the same. Right, and just to do a sanity check quickly, run the next two cells. Right, so everything seems fine. After this, you can skip over the next exploration part because we have already done this. I'm going to talk a little bit about the terminology. This was there at the end of last week's notebook, so I'm hoping everyone has read through it, but I still want to just quickly go through uh, what is here. So the first thing that we wanted to define was state, which is everything we need to know to make decisions. So state could be information about the environment or about the agent. And what exactly makes up the state will vary from problem to problem. It will also vary also vary across algorithms. So one algorithm might need a different set of uh, you know different different type of data, different type of information from another algorithm. So in this case, if you think about the algorithm, it has to take the ball and score a goal. So it's sort of trying to find the shortest path, and everything in the environment is actually static. So the only piece of information that needs to be tracked is the position of the ball, which we have encoded as a single integer between 0 and 20. So that happens to be the state. Now this is because we are searching for an algorithm that can just find a path, right? And we want the algorithm to just look at the ball's position and figure out the path. But if you think about it, more deeply, then you realize that if you want to make it more realistic, then probably you want the algorithm to also know about where your opponents are, right? That should help the algorithm find a better route. We're not doing that right now, but when you want to do that, then of course the state variable will change. It will be a tuple or an array or a list, and it will sorry, it will contain the position of the ball and the position of the opponent's position of the goal as well, perhaps. So this is how state changes. Uh, and in terms of actions, it's pretty clear there are only four actions. I'll skip over this one. The general setup is something like this. So this class is our environment, and it also contains an API through which an agent, which is going to be an algorithm, is going to interact with the environment. And what is essentially happening is that the agent is going to perform some sort of an action. Yes. So Hashim, this method is already defined, right? Or did we miss it last time? So this definition was here, is terminal state. It should be there if
Somehow it was not there in my notebook, so I had to pull in that code.
no problem. I'm just pinging it in the chat as well. So this should be there. Right. So yeah, so the setup is that the agent is going to send an action, and the agent is basically going to use this step API, which takes just one parameter, which is the action. This is how you interact with the environment. So the agent sends an action, and the environment, in response to that action, the environment will change the state. And the state, we have to remember that the state includes the position of the information about the agent as well. So agent is sort of part of the environment. So in this case, if you think about what is going to change, it is going to be the position of the agent. And also the environment will send back some sort of a reward, which we had defined, different integers for different types of outcomes, whether you are scoring a goal or running into an opponent or making a valid move or scoring an outside. So that is your reward. And this setup will sort of remain the same. The complexity of the problem will change, like I said. Later on we might want to make the opponents move as well, make them a little bit more intelligent, and we might want to spawn the player in different places on the field, so it doesn't spawn at the top left every time. So all of those things will happen, but this API, this setup is going to remain like this. Yep. I think that that's everything that we need to understand in terms of terminology, and we will pick up more pieces as we move through the course. So we'll get introduced to new words, new terminology. But for the time being, this is all we need. The other thing that we did on Monday sort of was that we defined four different paths, right? And now that we have an API, we wanted to uh, find out the cumulative we basically wanted to find out the sum of the rewards, right? So we wanted one number, which would be the description of how good the agent has performed, right? So we just sampled four different paths which are defined here, and right, and then we came up with this concept of return, which was like the sum of all the rewards that you get along a path, right? Very simple thing. So what we wanted to see is how the return changes as you change the reward. So one thing that we need to do today, and some of you might have done this on Monday itself, but we want to define this function get return, right? What it does is it will take one of these paths, and then it will just simulate this path, and at every step it will uh, keep track of the reward that the agent is getting, and just keep accumulating that reward, and then it will return that reward. That's all this is going to do. Just to get started, everyone please try to implement this method, and then try to run the next 4 cells and see how the reward changes from path to path. And you just need to simulate the agent moving through the environment using this tip API. So I think this is a simple problem. So we are not going to go into breakout rooms, but I'll give everyone about let's say 5 minutes, and see if all of us can get the definition right. So you have a path which is just a list of actions. We have to take those actions one by one, feed them into this tip API. The environment has already been reset, so you're starting from the beginning. So just feed the actions, and every time you feed an action, you get a reward and a next state. Uh, so you only need to capture that reward and add it to this return variable that we already defined here. And then if you want to debug things, you might also want to render the arena at every step. And then once you reach a terminal state, then you just break out of the loop. Okay, so this is really straightforward. So all you have to do is, if you're looking at my screen, so you just need to loop through the path list, and then just call a step, pass it the action, and you get the next state, the reward, and this flag done, which tells you if you have reached a terminal state or not. Then this is optional. If you want to render, then call foosball.render, and then you just accumulate the reward into this return variable. And of course, if if done is true, then you break out of this loop. Uh, so I wrote this code, and then when you run this with path one, so if you actually look at how the field looks initially, and then you look at the sequence of steps, then you'll see that this is like an optimal path because it goes east, then south, then east, then south, 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 and east. So it takes a shortest path from the starting point to the goal, and which happens to be 6 steps long. And at each of those steps, you get a reward of -1 because we set the reward structure such that there is a penalty every time you move to even if you move to a valid cell. So that is -6, and then eventually when you score the goal, you get +5. So the overall return in this case is -1.
Question: How do we get this new notebook? Because
Oh, yeah. So you, I'm I'm sharing the link in the chat. So you know the rest of the steps, right? You in Collab you need to go to File and then open Notebook, and then you go to GitHub, like this option, and then just paste the link that I just shared. Sorry, you don't have to paste the link. You have to select the repository. Oh, I'm sorry. Sorry, I shared the wrong link, but this is going to be, yep. So when you paste the link here and then you hit enter, then you'll see these options. You will see a drop down, sorry, a list of notebooks here. On my screen it's showing no results right now because I don't want to move away from the site, but you will see a list here, and then you have to pick the one which has W2S1 slash foosball. Does it work?
yeah, I'm just trying to save a copy and get it into my GitHub again, but I was able to open it.
Cool. Okay. So for part 2, again, if you try printing, you know, the return, then you can print it for part 2, part 3, and every time you get -1 because these are all sort of optimal paths. But look at path 4, it is a little longer. So deliberately we are going into a loop perhaps, or going up and down, so it's a little longer than the optimal path. And if you look at the return, so
Sorry.
is there a question?
Yes. Sorry, I didn't understand why it's -1 or -1 because when the ball goes like goes to a unmarked position, then it also get a -1, right?
Right. So if we start from here, if you can look at my cursor, so if I go east, then I get a -1. Then
Yes.
I go south, again -1, so that makes the return -2. Then -1 minus, so that makes the return -3. And then when you reach this point, you have -6 as your return,
Oh, okay. I
and then
understand.
you score a goal. Okay. The next thing we're going to do is to change the reward structure slightly. This is something we discussed earlier as well. Why do we want specifically this reward structure? Because in a lot of problems, we don't know what the immediate reward should be. for a lot of outcomes, we don't know how to reward or penalize the agent. And when we don't know how to do that, we will just set the reward to 0. Right. So this is the alternative reward structure that we just want to quickly experiment with. So there's already an API that we built to update the reward structure. Um, so just it will take you a line or 2 lines of code to do that. So please do that and then again run the next 2 cells. This time we're just comparing path 1 and path 4 because path 2 and 3 are similar to path 1. Yeah, giving everyone a couple of minutes. Please implement this and then again print the returns for path 1 and path 4.
So Farhan, I might be jumping ahead, but trying to get this reward, I mean, in our case, it is -1, but trying to get the reward to 0 is sort of like a minimization problem, right? Where you're trying to go to your goal and your goal is basically the minimum and let's say 0 here.
So one thing is that we are not going after minimizing the reward itself. We will try to minimize or maximize the return.
Oh, sorry. Yeah, the return, but the return is actually an accumulation of the rewards, right?
Right.
Okay.
So yeah, so you're going to be maximizing the return. That's right.
Maximizing the return. Okay.
Does that make sense? Because in our case, right now you saw for path 1 it was -1. For path.
Oh, because our rewards are in negatives. Okay.
Yeah.
Okay. No, but I'm just trying to get my head around from my other understanding of machine learning. Like going forward, reinforcement learning also is like a minimization problem where you try to somehow get to an
It will be, yeah, it will
global
be an
minimum to okay, reach your goal.
Right.
Okay, thanks.
So I'm just going to copy paste the code because it's really straightforward. Make sure you reset the environment. This isn't mandatory, but it makes sense because when you are implementing a new reward structure, you don't want to be in the middle of a game. Just reset the environment, and then you just call set rewards and pass this dictionary, and the rewards are updated. And then if I run the next 2 cells, so for path 1 now the reward is the return is 5, which makes sense because now the stepwise rewards are all 0, and the path we have taken it doesn't it is an optimal path, so it doesn't run into any of the opponents, it doesn't score an outside. So uh, the only reward, non-zero reward you get is at the end, which is 5. But if I do so for path 4, which is slightly longer, then again the reward is 5. Now this is a problem for us because we were just talking about finding the path which is optimal, which has the highest reward, and path 4 is definitely not optimal. We have shorter paths, but still the reward, the cumulative the cumulative sum of uh, sorry, the return or the cumulative sum of rewards is still the same, which is 5. That shouldn't happen. Uh, but you might say that this could be happening because we picked a certain type of reward structure where the intermediate moments were just given a reward of 0 and you only got a reward of 5 at the end. But this is a more general problem. Uh, and how do we address this? I don't want to go into all the details right now, but one way to address this is add something called a discount factor. And what that does is it sort of makes you a little greedy, so you pay more weightage to any reward that you are getting immediately, and you pay less weightage to any rewards that you'll get further in the future. And if you look at step 3 here, that is what we want to do. So earlier, if you look at this equation, earlier this equation was simply reward at time 1 plus reward at time 2. Forget about the gammas right now, but it was r1 plus r2 and so on. What we want to do is we want to introduce this factor of gamma, which is going to be a fraction. So you take the immediate reward that you're getting at this step, but when you take the next the reward at the next time step or the next step, then you multiply it by this fraction, which is going to be close to 1. You can make it 0.9, 0.99, something like that. But gamma is going to be that fraction. And then at the next step, it's going to be gamma squared. So it's even more discounted. So, the reward that you get 2 steps down the line has much less influence than what you get right now. And you can imagine that because this is, it has an exponent, after a few steps, this will be really small. So any rewards that you get farther and farther out in the future, uh, they do not contribute as much to the return as your immediate rewards do. And what this will do is, and we will just run the code and verify this, but what this does is that anytime you take a non-optimal path, the uh, the return is going to be lower than when you take an optimal path, because in case of an optimal path, the powers of gamma are going to be much higher. So what you need to do in this cell is implement this strategy. So once again, we are finding the return. The only thing that has changed is that now we have this discount factor gamma. It's a hyperparameter, so right now we're not bothered about getting it right. We can just set it to 0.9 or 0.99, and but we do want to have this control over this. So you have to implement that logic here, and then in this cell I'm setting gamma to 0.9, and then we are running the same computation again, but this time trying to find discounted returns, and we'll see how the discounted returns are in agreement with what we would expect intuitively, that a shorter path will have a higher return, a longer path should have a lower return. So again, everyone can take a few minutes and implement this. This can practically be copy pasted because the loop and everything is the same, but then you have to factor in this multiplier here and here.
Shouldn't the default gamma value be 1?
Yeah, gamma should start with 1. You can think of gamma being 1 for this term. You're saying gamma
In the
default?
function, the default is assigned
Yeah, so
0.
if you make gamma 1, then you're not discounting, then it's the same old return that we just saw, right? If gamma is 1, you're just adding up RT1, RT2 and so on.
Yes, but I was talking more about the function implementation, where if you don't give a value for gamma, then it will be 0. And giving 0, it means that you don't care whatever happened before, which is a bit strange.
That is right. So when you make it 1, then this corresponds to the previous case, right, where we were just adding up the rewards. But if you make it 0, then it doesn't even work, because you are just not considering anything that you get after the current step. So we want to keep gamma somewhere in between, where you are paying more weightage, more importance to the most recent reward, but then subsequent rewards are also getting they have some influence, some control over how much return you get. Okay, so I'll copy the code again because this is very similar to what we just saw. So this discount coefficient that is initialized to 1, this is the multiplier. So initially it's 1, then I'll multiply it by gamma in the next step, so it becomes gamma, then multiply it again by gamma and becomes gamma square. The rest of the loop is same, but here on line 9, when I'm computing the return, then I'm multiplying my reward by this discount coefficient. Of course, the coefficient itself gets updated every step, starting with 1. So I hope this is clear. If there is any confusion, let me know. But with these changes, if you run the cells again, so in the first case, when you pick the optimal path, the return is 2.66. In the second case, the return is 2.15. The second case is path 4, which was longer by 2 steps. Now this makes sense. This is in agreement with what we were thinking, that if the path is longer, then the return should be lower. Is it clear to everyone? Is there any confusion at this point?
So is this kind of like regularizing to try to get to a shorter path?
Yeah, I don't think we can call it regularization because that is used in a different context, but it is definitely some sort of, they call it discounting. I can't think of another equivalent term, but the idea is same, that anything which is like more than a few steps away, that has very tiny influence on your decision making, because your returns are not influenced, so you don't care about what happens, say 10 steps down the line. Okay, so now that we know this bit of terminology, we just want to formalize the problem a little bit more. So we have the whole setup, agent and environment and everything. And what we wanted to do is we wanted to score a goal. We still want to do that, but we want to get the highest. We can synthesize the whole problem in a single statement and say that we want the agent to get the highest discounted return, right? And that would eventually mean getting scoring a goal, because if you don't score a goal and you just wander here and there on the field, then you, because of the discounting in effect now, you are just wasting time, and that will get you a lower return. So to get the highest possible return, you have to score a goal, and you have to go there through the shortest path, right? So now the question is, how do you do that? Of course, there are, we discussed this earlier too, this is a very simple problem. You can pick any shortest path algorithm, and because we know that this is actually a shortest path problem, we can use that algorithm, and we can find a solution in exponential time, uh, which is good. But that is not the idea. We want to build something more general, because when the problem evolves, when we have more, the things become dynamic, the players start moving, the actions are not perfect, there is some imperfections, some probabilistic actions are there. So when you try to move the agent right, it may not go right 100% of the time. It might slip and go into the cell below some of the time. So when stuff like that starts to happen, then your shortest path algorithm will typically not work. So we're not going to invest time in exploring shortest path algorithms. We are going to take a different approach. Um, we know, we formally understand what the problem is. We want to find the path that gives you the highest return, right? So the simplest, most brute force thing we could do is just enumerate all the paths, and then we have that function that calculates the discounted return for every path, and you do that, and then you order them by the return you get, and the one that appears at the top, that is the path you want to take. The problem is that even for this simple game, toy problem. There are a huge number of possibilities, a huge number of paths, because you can imagine that when you start at the top left, you can make 4 choices. You go right, left, top, or bottom, and then at every subsequent step in your path, you again have these 4 choices. You can add a few constraints because there are some invalid moves and stuff, but roughly you have 4 choices at every step. And if you start calculating the total number of choices, things multiply, and then all of a sudden there are so many choices that you cannot even enumerate them. Calculation is still a far cry, but you cannot even enumerate those steps, right? So if that is not possible, if we cannot enumerate all the paths, and if we cannot just calculate the discounted returns, what is the second best thing that we can do? And this is where you start to think of the similarity this problem has with many other dynamic programming problems, the problems that you can solve with dynamic programming. These are typically problems that break down into smaller problems, and if you just look at the number of problems that you might have to solve, that is exponential. It takes the form of a tree, right? So this branching and more branching and more branching, and you have a huge number of smaller problems. But the good thing, wherever dynamic programming is applicable, is that these smaller problems, they are not independent, they overlap, so you're solving the same problem again and again. So dynamic programming basically solves a very small problem in algorithm, which is, if you are trying to solve the same problem again and again, then you can just cache the result and not bother recalculating. So what happens is, if the true number of individual sub problems, the smaller problems, is polynomial, then you can just cache everything, and you have to do a polynomial number of steps. You don't have to do an exponential number of steps. That is roughly what dynamic programming does, right? So if we want to look at this problem more closely and see if we can use dynamic programming here to calculate the returns, and we want to find the return for the path with the best return. So one thing that you will notice is that all the paths, no matter how many paths are there, they are all made of the same subset of these 80 state and actions, right? Because there are 20 states and there are 4 actions. So pick any path that is going to be like, if you go to path 1, right? So right here, so this is path 1. This, it doesn't contain states, but that is implicit because we always start in state 0. Then it says that we have to take action E and go east, which will take us to state 1, and then take action south, which will take us to state 5 perhaps. So uh, so these are the state action pairs that this path is composed of. And you can say the same for path 2 and path 4, but any of these state action pairs that appear here, they have to come from the same possible set of 20 states and 4 actions, right? Uh, that is that is true of all the paths that we have considered, and all the possible paths too, right? uh, so what we want to do is that, let's, for the time being, forget about calculating the path with the highest discounted return. What we will try to do is we'll try to find the highest discounted return for each state and action, right? So we'll forget about which path we are taking, but if we'll just think about cells or positions in isolation. So suppose I'm here in this cell, second row and second column, then I just want to know what is the maximum return that I can get for each of the actions in this cell. So there are 4 actions. So for corresponding to going east, south, west, north, I want to find out what is the best return that I can get. What is the highest return that I can get, right? Uh, and then we'll slowly think about, if we have this information, then how can we construct the path that gives us the highest return, right? So how we are going to do that? It's simple, because the state action pair there are 80 possibilities, 20 states, and 4 actions. So we are going to store that information in a table. We'll see how to compute that information, but we're just going to store it in a table. In this code, we are using a pandas data frame because it's easier to read. The code is more readable if you use a pandas data frame, but if you want to make it more efficient, then perhaps you would use a NumPy 2D array, right? So we want to build a table which has the best return for every state and action pair. Before we do that, we'll build something simpler. So if you go to step 4, there is some code already. I'm going to explain what that code does. So right here, we are constructing a table, right? This table has states along its rows. So there will be 20 rows and actions along its columns. So there are 4 columns. If you run this code, this is what we get. So these are the states 0 through 19, and at the top you have the columns N, E, W, and S, and everything in the cells, everything in this table is set to none. We don't know. Yeah. So for the time being, everything is set to none. So this is not the table we have to construct. We want to construct a table for storing returns, but I'm just showing you an example of how to do it for the rewards, right? So this is what I'm calling my rewards table, and then the code right here. This is just visiting each cell in the table. So I'm looping over the states. Rewards table. Remember, this is a pandas data frame. So every data frame will have a field called index that lets you basically access all the indices or all the rows of that table. So that is what this for loop is doing. And then I'm just checking if that state is a terminal state or not, because there is no reward for terminal states. So if it's not a terminal state, then I'm just looping over the 4 possible actions. The actions come from the column variable in the table. So just looping over the actions, and then I'm calling these two. I'm calling this API get next state on action. I'm passing it the state and the action that I'm currently in, and it tells me what the next state will be. And then I'm using that next state to pass it to this other API, which also tells me what the reward is going to be. And because I wanted to store the reward, I'm going to write it back to this location, state and action. So let's run the for loop. And this first line in the next cell, this is just creating a list of all the terminal states, which is all the states where there's an opponent plus the goal state. So this is that list, and then I just print the variable, the table that I just constructed. So this is the rewards table, but now it has been filled up with the appropriate reward. So for state 0 and action north, remember north means going up. From state 0 there's no going up because you're scoring an outside, so the reward is -1. That seems right. And from, for example, state 1 and action east, this would take you to state 2, which had an opponent, a defender there, and the reward was -5. So that is also reflecting here. So just try to run these 2 cells and see for yourself if you are also getting the same result or not.
Why there is none?
Why are there some entries none?
Yeah.
Yeah. So when you are in terminal state, you just can't take any action. You're trapped there. The game is over. So it makes sense to define it as none or something which is not a number.
Okay.
So none is for the opponents, like if you're on top of an opponent?
Yeah, if you are in the goal state or on top of an opponent.
Okay. Also, is this basically what we're doing here, just like a Viterbi decoder, essentially?
It is similar.
Okay.
It is. But I just want to make sure that everyone is comfortable reading this code, because um, pandas is not necessarily essential for implementing these algorithms, but it keeps the code clean and very readable. So this whole thing, we're able to print it and see states and actions. It will be some additional hassle if you were using list or numpy arrays.
So is none kind of like saying infinity? Like basically over there, the shortest path is, basically that's not a path you can take.
It is undefined, so you can, I think it should be set to NA or something, which is more appropriate. But in this case, I just set it to none. You can set it to infinity, but then you have to you have to be careful when when we build the returns table and when we update things. You have to be careful about how and when you want to exclude those cells from your calculations. Because there will be calculations where you don't want to include these terminal states. Right. So I'm hoping this is working for everyone. If there is a problem, let me know. But now we really come to the first step where you have to implement something bigger. So we just constructed a table which stored the reward for every possible state and action pair. Right. Now we want to do something similar, but for the returns, right? Because returns is what we are after. We want to find the return for every state and action pair. Right. So just go through these steps here very quickly and let me know if there is any confusion, and then we will break out for some time and we'll try to implement this function over here, which will again create another table, but this will be filled up with the returns, not the rewards. And for the time being, we don't we are not going to calculate the returns. So all of that is mentioned here. We are just constructing an empty table right now. Okay, so I'm going to assign everyone to breakout rooms again. We will have around 5 minutes. This is a very simple and straightforward implementation, but it will be sort of a warm-up for everyone. So we're going to break out rooms shortly. Cool. Were there any issues? Anyone faced any difficulty implementing these two lines? Right here. So the table is constructed pretty much the same way as we did for the rewards table. And then you just set the return for the terminal states to 0. Uh, Anyone figured out why we want to do this? Does it make sense intuitively? Like, if you think about it.
Right now for the reward system you're using, we're still using the one from step 2, right? How we are setting the unmarked to be 0. Like when we're running all this in step 2, we change the reward structure so that unmarked is set to 0 instead of marked.
That's
But-
right. We are yeah.
But do we want it to be 0?
We sort of want it to be 0 because, like I said, that is something we want to experiment with. Because in a lot of scenarios, you won't know what reward to set, and then you'll end up setting it to 0. I have set it to 0 in my code. Feel free to set it to the previous reward if you want to experiment a little bit. I think for the rest of the code today in the classroom, we can keep it set to 0. But then it's a good idea to also switch it back to the older reward that we had and
Yeah,
run
because
through
by
that.
setting it to 0, what we are saying is it's okay to make many moves where we move to unmarked region, right?
No, it's still not 0. It's not still because of the discounting. So
Yeah.
any additional moves are still being penalized, right?
I see. Okay. Yeah.
So that is what we did when we implemented discounting. Then we printed the returns for path 1 and path 4, and path
Mhm.
4 had a lower return despite the reward being 0 at every step
Yeah.
because path 4 was longer.
But even if we set it to -1, we should see that similar
Right.
reward.
For -1, obviously it will work. 0 was trickier because the immediate reward was same. So then how did you compare the two?
I see. Okay.
So I'm hoping this code is working for everyone. Just to verify, I'll run the next two cells. This is mostly filled with nulls except for terminal state for which the return is 0. And my question was, why do we want the return to be 0? Did anyone happen to think about why we want to set the return to 0?
Which part should be 0?
So we are setting these state action pairs are being set to 0, right?
Mhm.
For example, 2 is a terminal state, and so is 7 and 9 and others and 19. So for all these states, I'm setting all the rewards to 0 for the terminal states, right?
To discourage from use that state again because there is no reward.
Right. Sort of discourage as well. And I mean, once you are trapped there, you can't really carry out any action. So you can't. So reward is undefined, and return can be made 0 because we'll see in a moment that we will use these terminal states in our dynamic programming setup. So we'll use these states to terminate the computation. So it makes sense to give them a numerical value, which doesn't contribute to the return, but it's still a number.
So what is this from dict function doing? It's going through all these state and action pair.
Yeah, so it's just constructing. So if you look what is inside there, this is a dictionary, right? So you have state on the left hand side, and
Yeah.
then you have this dictionary which is on the right hand side, right? So this from dict is just converting this dictionary into a pandas data frame. And there are many ways to do this. You can create the same thing from a list of lists, from even numpy arrays, but this is sort of more readable because if you look at this code, this says, I'm taking a dictionary where the key is the state, and then the value is this entire thing, which is mapping different actions to none, and then you're taking this thing and then you're converting it into a pandas data frame.
Farhan, could you go over again why the terminal states are set to 0?
Yeah, so terminal states are set to 0 because when we are going to, in the next step, we are going to recursively compute the returns, and we are going to use dynamic programming. So, there has to be some halting condition for every terminal state because that is where the computation has to stop. So it makes sense to initialize like with any any sort of recursion or dynamic programming. When you're doing that, for every terminal state or for every stopping state, you will have some hardwired value, right? For Fibonacci it could be 1 or 0 depending on where you start. So that those values, whenever we encounter them, we are going to stop the computation there. For other states, we'll be computing the values ourselves.
Oh, okay. All right.
Cool. So let us look at step 6, which is like the crux of everything that we're doing today. So and now think about the setup. We have this these cells, these different positions, and the player can move through them. And what we want to do is we want to find the best return, the maximum return that you can get in every state for every action, right? So not only for each state, but for every state and action pair. Why this is important, we'll come to that a little later. But for every state action pair, I want to find the best return that you can get, right? And if you formulate this as an equation, then for every state and action pair, I want to find the return. um, but return, how are returns computed? They are computed in terms of the neighboring cells, right? Because computing a return means going through one cell to the next and next until you reach the goal. So this is, you can sort of break up this computation. So there is the immediate step when we move from this state and this when we are in this state and take this action, then you go to this next state, right? And there is an associated reward with that. That is this term reward. It's a function of your current state and the next state. And then when you are in the next state, you also want to find out there are four possibilities. There are four different returns associated with that state because the state has four different actions. So in next state, you can in future you might take action north or east or west or south. There are four different possible returns, right? And what we want to find is, so this reward part is fixed. Once you decide which action you want, which state action pair you want to explore or fill up in the table, this reward automatically is fixed because you can only go to a certain fixed state t plus 1. This is fixed. But we want to find the maximum return, maximum value for this left hand side. So over here we are applying the max function over the over the return values of the next state. This is really important to understand. This is quite natural. If you think about the 2D grid, the return of a cell is inevitably linked to the return of its adjacent cells, because any path on which this cell falls will contain any of these four cells, right? So this should make sense to everyone. If it doesn't, please ask me right away. This gamma is upfront because we want to discount things. So we take the entire immediate reward, but then the return in future, that is discounted by gamma. Does this is this making sense to everyone?
This is the classical Bellman's equation. Or this is no. This is a part of Bellman equation, not again.
This is yeah. So this can be derived from the Bellman equation, uh, but yeah, we are going in that direction. And this is, I mean, even if we don't know about what Bellman equations are and which one this one is, uh, this should intuitively make sense to everyone, because when you are talking about shortest path or returns or whatever, and thinking about this 2D grid, there are only four possible ways out of a cell. Uh, those are the four different neighbors, and this is the return. These are the returns that you can get by following those four actions. The maximum of these four plus the reward is what you want to store in this cell.
Okay. So like as compared to this, like the reinforcement learning based approach for the shortest path, and also some other algorithms like the A star algorithm, which gives the optimal path. I mean, there is no such anything like the A star is better, or it's kind of depends upon scenarios.
So that is what I said in the beginning, that A star and algorithms will work in a very limited sense. When most of the things are static, then you can use A star, right, or the external algorithm. But yeah, but as you make the world more complex, make the game more complex, if things are dynamic, if your actions also have some probability involved, then you cannot even use those algorithms. So it's not a fair comparison between A star or reinforcement learning, because obviously if the problem can be solved with A star, you don't even want to explore reinforcement learning, because we will see that these are going to be estimates. They're not going to be exact solutions most of the time.
Hey, Parag, this is Mani. I want to understand the maths part of this equation, right? So the way it is written, it looks like when you compute the reward, it is going from state t to state t plus one. But when you compute the max, it always takes the max return. So what I am trying to understand here is, no matter what state transition you take from t to t plus one,
Right.
the max is always among all the four possibilities, and you take the max. So for example, let's say you're going from north to east is the state transition that you're doing.
So
Then the reward
sorry,
is,
sorry, I'm cutting you off, but not to east. I mean, north and east are different actions. So the states will be something like, if you are in state 0 at the top left, and then you take action east,
oh yeah,
you're bound to go to state S1 or state 1, which is to its right. So that automatically, the moment you
got
fix
it,
the
yeah.
action, that automatically fixes the state, the current state and next state there, right?
Yes, sorry. So let's say I'm going from, yeah, so state 1 to state 2, and then I take some action either north or so what I'm trying to understand here is, okay, so I am going from state 1 to state 2, and let's say that action change needed is north to east. Then here you will uh, okay, let me put it another way. Uh, Basically, my question is, no matter what the state transition is, are we always going to pick the max? Or it's the other way. You first pick the max, and then that becomes your state transition.
Okay, so actually that is thinking one step ahead, where we will use this information to make transitions, if I'm understanding your question correctly. So
Okay.
right now, the way this works is, I'll go back to the example. So let's say I'm in this cell, right,
Mhm.
highlighted over here, right. I want to find the best return that I can get in this cell,
Okay.
right.
Okay.
Now I know that there are only four ways out of this cell:
Mhm.
top, left, right, and
Mhm.
left, right, top, and bottom, right.
Mhm.
So I'll pick one action at a time. So I'm trying to find, let's say, the best return for action down, right, action
Mhm.
south,
Mhm.
right. Now once I fix that action, I know that I'm going to end up in this cell right here.
Okay.
Correct. So now how do I find the best return? I know that I'm going to make this transition. I'm going to go down. So there will be a reward associated with that. So I'm definitely
Uh-huh.
going to accumulate that reward. But then I also have to find out what is the best return for this cell where I ended up landing, which is my next state. So what is the best reward? What is the maximum reward that you can get? And then again, you have to think that there are only four possibilities: going up again, or going right, or left, or down, right? And that is what you see here in the equation on the right hand side. Because on the left hand side, we are only considering a state action pair, but on the right hand side, you have to consider all 4 state action pairs.
Oh, okay, I see. So for the future, you're okay.
Yeah, for the future, you have to consider all 4.
Okay.
And once you have this table filled up, then you will use that information. Then at that time, you will see which is the best action and which direction you should go into. That is sort of the 6, following step.
So
Okay.
I have a follow-up question for that. So we took out the maximum return state. Is that going to be in the first term? The state t+1, that would be the maximum.
Could you repeat that? Is that going to be?
So you have the first term, reward state t and state t+1. Right. So is the state t+1 the maximum?
State t+1 is fixed actually. The moment you fix action t, the moment you fix the action t, this variable, right? So I just showed an example, right? When I was in that cell and I said I'm going to compute the reward for action down. So once you say you have picked action down, then obviously the state is going to be fixed. There is no maximum. There is no other possibility, no other option here. This state is automatically fixed.
So is that okay? My question is, when you are calculating the maximum, you are choosing one of those, right? Whether you have to go the north, east, west, or south.
Right.
So if you choose south, is state t+1 the action south?
So if you suppose this gives me the maximum return, right? This possibility. So I'm not actually going to execute that action. I'm just testing. I'm just looking up what is the value in the table corresponding to this state and action pair.
Okay.
So I had the same question which was asked right now, and I'm going to try to see if I understand it in a different, rephrase it. So this return state t is, let's say if you're at the starting position, which is 0.
Right.
That means, so this equation means that you have already taken step 1. You are at step 0, you have already taken step 1, but you're trying to calculate the maximum return for taking the step 2.
I'm trying to calculate the return for the step that I just took. The first
so we are still calculating return for step 1.
Right.
And not step 2. Okay.
Not step 2, no.
So what does, so what does reward state t and state t+1?
Yeah, so you just took the step, right? The first step going from, let's say, the 0th step to the first step, 0th cell to the first cell. So this is the reward corresponding to this transition.
So I took it already, or am I still calculating what is the best possible first step?
Yeah, so you don't necessarily need to take the step. That is not what we're doing here, right here. You just need to look up the reward from the class that we have, right? So
Farhan, to avoid confusion, right? We can do this without having gamma star max, right? And then you are adding that, making sure that we are heading into the right direction. They are adding a fraction of future reward to the existing reward, so that we head into the right direction.
So how would you do it without gamma max?
I mean, if you don't take gamma star max, then it would be like a plain, you're going blindly, like, okay, this will be the next one, and this will be the next one. You might hit into the, like, what do you call? You blindly hit it to the terminal or whatever it is. Yeah.
Right. So, yeah. So there are a few questions which will actually become a little clearer as we repeat this and we play with different algorithms, because there are different ways of doing this. The one solution that we are trying right now based on pure dynamic programming, we are cheating a little bit because we are actually looking inside the transition matrix. We are looking at the values, we are looking at the rewards that this environment has to offer, which is generally not the case. So there will be situations where we will actually simulate the environment, we will take these actions. But right now in this tabular approach, you don't need to simulate anything. You don't need to call the step API. We will see how, like in the next few steps, you'll see how this is going to happen. But if we, if we hadn't this specific problem in mind, if we were just looking at this 2D grid, and then every position on the grid had a return variable, and we knew how reward and returns were connected, does this equation intuitively make sense or not? So like just for the time being, we can stop thinking about how we are going to compute this. But let's say somehow we have returned for these state action pairs, and we know the reward for this state and next state. Then does this make sense? Because what I just tried to show through an example, that if you are in a cell and you pick an action, then if you're going down, you know what the next cell is. In that next cell, you want to find out what the 4 different returns are. You want to pick the maximum of them, and you want to add it to the reward for the transition between the current cell and the next cell. Is there any confusion with this setup?
So will we replace reward state t plus 1 with the same max function of the north, south, east, west?
No, we are not going to compute rewards. Rewards are inherent to the environment, right? So we are not going to do anything with the rewards. We will store the returns. But what you are getting here on the left hand side, this is supposed to be stored in the table that we just constructed.
Oh, this is very far. That's okay.
So reward is a property of the environment, right? So we don't need to compute reward. We can just look up. We can ask the class to tell us what the reward will be for a certain transition. It is fixed. Return is something that is dependent on our actions, and we want to compute returns. And that is what we are doing, but we are doing it on a cell by cell or a state by state basis. So we go to every state, and then we try every action, and then for each of these pairs, we use this equation to sort of compute the return for this state and action pair in terms of the state action pairs of the next state. Okay, let's give it a try. Yeah.
Sure. Sorry, one quick question. If this function is meant to represent discounted return, shouldn't gamma be to the power of t?
Yeah, so gamma is not to the power of t, because so you already have returns, right? These 4 are returns, right? So we are assuming that all the higher powers of gamma, they are already accumulated. We have somehow computed the returns from state t plus 1 onwards. We just need to compute the return at state t, which will mean taking one step. So this will be your immediate reward, and then whatever you get next, you can actually, if you go back and look at this equation, the one we had for returns, right? Discounted returns. So look at this equation, right? Now this is the reward that you see down here in the equation that we were just looking at, right? Now if you take this gamma outside, this gamma, right? So you're left with RT2 plus gamma times, so all these powers will be reduced by 1. So this will be gamma times RT3 and everything. So if you look at it more closely, you will realize that this is actually the return starting at state T2. You can do it with pen and paper. If you just take this gamma outside, and then you're left with RT2 here only, and this becomes gamma times RT3, and this becomes gamma to the power n minus 2. So this is essentially the return starting at step 2. And this is exactly what we have here.
Got it. Thanks.
So max return state t plus 1, and whatever action you take is actually return t plus t2.
Right. So if you think about these transitions, these are between state t plus 1 and t plus 2.
Okay.
That is, you have to do that. You have to look, you have to peek into the future, because eventually returns are based on going from one cell to the next cell. So you have to think about future transitions as well, because returns are based on a path, and that means you have to keep going from this state to the next state to the next state. The good thing is that we are assuming that we already know the return from state t+1 onwards. We'll see how to do that, but we are assuming we already know the return. So this is, you don't have to recompute returns by going through the entire path, right? So assuming that you have the returns for state t+1, for a new state t, you can use this equation. Cool. So what I'll do is we will try to implement the function. We will try to implement this equation as it is in the form of code, and then there will be some issues. We'll hit some obstacles, but eventually we'll try to implement a version of this equation that is working, and then we'll try to make sense of how it is working, how it is updating the cells. So I think I'll create breakout rooms again.
Farhan, I
Again,
have one
yeah,
question. Sorry.
yeah.
So here in this equation, we know the return gets computed, but the reward, I'm just trying to understand, like the reward is still engineered, right? So you like
Right.
predefine what the reward should be.
Right.
But
so the reward,
yeah, but in general case, also we expect the designer to actually engineer
yes.
the reward, or is there some kind of an way to
No.
learn even which one to, how the reward can actually be defined?
Yeah, so I'm sure there is some research around how to sort of figure out the reward, but generally, if you look at problems which have been solved, the rewards are engineered. They are
Okay.
generally simple. I'll show a few examples in the upcoming
Okay.
sessions. But you have to engineer that, and then you have to fix it. And assuming it's right, it doesn't have any logical flaws. Then you have to sort of spend all the time figuring out how what the returns are and how to optimize the returns.
Got it. Thanks.
Sure. So I'm going to open the breakout rooms again. Just look at the to-dos here. It should be simple. This equation, this has to be translated in the code as closely as possible. So it will look pretty much like the code. So I think 10 minutes should be enough for implementing this. Let's see.
I have one question.
Yeah.
So what is the gamma number here? It looks like it's not defined, or it's not
It
positive.
was yeah, so it was defined.
2.9?
Maybe it was 0.9. So I actually defined it as hyperparameter right here. Maybe I missed explaining this cell, but I fixed it to 0.9.
Okay, yes, okay. Get discounted return. Well, my question is, so this is in a function, right?
No, this is outside any functions. This is at the top level.
No,
right?
no, I am talking about a compute return v0.
Right.
That one you cannot see the parameters of hyperparameter.
You can. It's a top level variable. It will be visible inside the functions too.
Oh, it's still like even I'm inside the function, I can still see the.
You can still see the top level, right?
Okay.
It's not a very good practice, using global variables like this, but because it's sort of a configuration or a hyperparameter, I think for the notebook it makes sense to just put it at the top level and it's visible to everything.
Okay, thank you.
Sure.
Oh, why do you define it to be global variable? Like,
yeah. So yeah, we did. So what other options were there? Because there are lots of functions that are going to use this variable.
Yeah, I understand that part. My question is, like, what keywords do you use to declare it to be global?
You don't have to do anything extra. I mean, if it is inside any function or any other block, then it's a global variable.
Okay.
So same thing for the rewards table, right?
Yeah.
Okay.
That is also because we are going to use it across the cells, so it makes sense to just define it outside. And this is something that you have to be careful with in the notebook. So If you're using the variable again, if you're updating it, which we are doing with returns table, then you have to careful like which definition you are using. If you skip over a cell, then you probably end up using an obsolete value, stale values.
Hi, Farhan.
Hi.
Hi, this is Chris. We were in a break room with just only two people. Was it the correct thing, or we were in there for a while without really talking? So I thought maybe there was something going on in the main room, so we just broke out of the break room. But
Yeah, I think so some participants didn't join the room because there are 6 rooms and there are 4 participants per room. So
okay,
I think some of you might not have joined the room. Perhaps that is what was happening.
okay, possible. But yeah, was there some conversation going on in the main room like that we missed, or?
No, there wasn't because I'm practically waiting for everyone, and then I'll start, hopping into different rooms and asking if everything's fine.
I see.
So, if you want, you can go back to the room, but if you want to continue here, that is also fine.
I guess I'll just continue here. I guess there was just like 2 of us in the break room anyway.
I do have a quick question.
Yeah.
So when it reaches the maximum recursion depth, seems like even if I set debug to true, it's not going to bring out message. Is that expected?
Your voice is breaking up. Could you repeat?
Oh, okay. So can you hear me now?
Yeah, yes, it's better now.
Okay. So I'm saying when I reach the maximum recursion depth,
Yeah.
even if I set debug to true, it doesn't seem to print out any message. Is that expected?
Yeah. So if the stack, it's this practically a stack workflow. So I think that
Uh-huh.
might be the issue. Could you share your screen and show me what's going on?
Oh, okay. Sure. Can you see my screen?
Not yet.
Can you see it now?
Still, I can't see it. I just see the blank screen and the different participants.
Let me try again. Yeah. Okay.
Yeah,
Okay.
yeah, yeah. It was coming up.
Oh, can you see it?
Yeah.
Okay. So I don't know if I had the correct code there, but I reached this maximum recursion depth.
Right.
But then, even though I set, so when I call it, this was set to true, right? But
Right.
it doesn't seem to print.
It
Print.
should.
It should.
It's weird.
So maybe it's
It
some.
should be printing, yeah.
Okay, then maybe it's
One second.
something else.
Names.
And maybe there's some other
No,
bugs
it
in the
should.
code.
There's no reason it won't print. Can you try running the cell again? This is weird because it does take some time, but as
Maybe the way that I write the code is not. It's not. It's something.
I don't see any issues with the code.
I think you should put the recursive statement after the if debug print.
Oh yeah, you're right. Yes.
Oh yes.
All right.
But I tried that as well, but like even so, it only prints 2 times.
Okay.
Oh wait, what? All right.
All right. Yeah.
Right. So this is going to be a lot of output.
But the state is not changing.
Yeah, and that is what sort of we have to figure out.
Oh. Okay. All right. Guess yeah. Thanks for the suggestion.
Sure.
I'll stop sharing.
Okay, so were we able to figure this out?
So where I was getting stuck was that my frame was being populated with NaN instead of none, so it wasn't going into that first guy. I think one other person in my breakout room was mentioning that if I use your code, I'll get nuns, but mine was giving me NaN.
So there could be NaN is unlikely because we are not doing any numerical computation here except for taking the max. But let's see. Let's see. I'll try to explain what the solution should look like. So up right on line 4, we already have the next state. All we have to do is add this line, which is using the other API, again passing it a state and next state, and you get the reward. This debugging line was already there, which will help us debug in a moment. But then the update, which is like the dynamic programming or the recursive part of the equation, that should be pretty simple, something like this. This is sort of a one-on-one translation of the equations we wrote. Right. Just look at this part carefully, and then we'll talk about the errors we are getting. But this is what we have on the left-hand side. So on the left-hand side, we had the return that we wanted to store in the table for a state T and action T. So this is what it is. Right. This is a pandas data frame, so you will perhaps want to use the LOC, which stands for location. So use LOC to update the table. So inside here, you pass the parameter current state and the action you took. Right. Then you have the reward, and then you have gamma, and then we are just taking the maximum of the 4 future actions that are possible. And how are we doing that? We are just recursively calling the same function returns v0, but this time for next state. So instead of state, we are using next state, and we are switching between the 4 different possible actions. That is all that is happening here.
Quick question here. So should we compute, so in the here line 5, you're computing the immediate return reward for transitioning to next state using the built-in function. Should we make the use of the table we built earlier, or should we actually try to interact with the false
Yeah,
here?
so we did build a reward table, but we didn't really populate it for this purpose. It's either way, it's fine because reward is something that is static. So you can either use these APIs or you can look up the table. That is also fine. Okay. So if everyone has this code in place, but if you still try to run the code in the next cell, and if you have debug set to true, then this is what we get. So it says maximum recursion depth exceeded, which means there's something wrong with our recursive equations. But if you actually read through the logs that we have added, you see a single, this triple, this is all you see, 0 and 0. And if you look at the log itself, so it says trying to fill, so you have a state, then action, then state. So we are trying to fill fill up the table for state 0, action not, next state 0. Obviously next state is going to be 0 because action not just takes you outside the field, which is not going to happen. So this is what is happening. But could anyone figure out why this is happening?
So when you move toward north on state 0, it returns next state still as 0, so it gets stuck in there.
Right. So this is sort of bound to happen because we are using recursive equations, and you don't see any terminating conditions here, right? So anytime there is a transition that takes you from from a state to the same state, which happens for all the terminal states and invalid states, so all of those are going to create problems. So that is the root cause here. Uh, because of these debug statements, which were sort of put in the right place, we're able to quickly figure out that this is what is going on, and this is something that we'll try to uh, fix in the next cell. But does this piece of code make sense to everyone? This was a first attempt. This is not perfect. This has flaws, but this is just a translation of this equation into code. Okay, we'll spend some more time on this one, so we'll slowly understand this even if you don't do it right now. So there is indefinite recursion. We know that it is crashing because we are revisiting the same state. The question is, what should we do about it? If we are going back, if you want to compute the return for a state and one of the action takes you back to the same state, then what should we do about it? One of the things we can do is just we shouldn't allow, because this is a loop, right? And we know that anything that has a loop is not going to be an optimal path. So we can sort of try to nip it in the bud. So the moment you see that the next state and the current state are the same, there is no need to try to find the return, because that will just create an endless loop. And what you can do is, but you still need a value to put in the table, or substitute in your computation. So what could be done here is that you set it to some large negative value, like negative infinity. So your computation, your equations still make sense, but you don't actually have to recursively call the function with the same parameters, right? And that is what you sort of can do here. So it was supposed to be, give me a minute please. So what we want to do is catch that condition the moment you detect that yeah.
But I think the whole problem is because the get next state on action, if the state is not valid, we return back the original state.
Yeah, that is right, but we don't want to modify that, because that is the sort of behavior that we want to implement in this environment. That if you are trapped in a terminal state, then there's no way out. So that is
I
going
see.
to happen. We want
Okay,
to sort of find a way around it in our code.
got it.
So how we'll do that is with a small modification, practically these two lines, which is just catching this condition, right? If next state and state happen to be the same, then you just install this value, which is minus infinity for your return, which also makes sense, because if you are caught in a loop, then you're just going to keep looping and looping and looping, and your reward is going to drop every time you loop. Your return is going to drop. So it makes sense to set it to something which is smaller than anything else. So I sort of did that here because it was a small change. Uh, but I just try adding this line to your code as well, and then run the next cell. So just check if next state and current state are the same, and then just don't do anything else. Just set it to minus infinity. Right. Let's try running the next cell. Okay, we still get a maximum recursion depth exceeded, which means there's a stack overflow. Stack overflow happens when you are running out of stack space because you're calling the same function again, and it just keeps increasing the size of the stack until it runs out of the maximum memory that can be allocated for the stack. But again, sort of the same problem, but now if you look at the logs again, and this will require some scrolling, lot of scrolling. Yep. Yep. So if you manage to scroll to the top, you will see what is going on. So it's going to this part. It says trying to fill 0 not 0. Okay, the self loop has been caught, so it shouldn't cause a problem. Then it says it is going to 0 east 1, which again makes sense because 0 not 0 is immediately filled with minus infinity. So the next thing that will happen is you will try to fill 0. The next action is east because we have north, east, west, and south. So 0 east, and that takes you to state 1. So that is what that gets printed here. That also seems to be working. Then because you have ended up uh, in state 1, you would want to, because of the recursion, you are going to try to fill up all the different actions for state 1, which means 1 north. 1 north again brings you back to 1. It's an immediate recursion. This is also called, seems to be working. Then you try 1 east, and 1 east takes you to the second position because you took first 0 east 1, then 1 east 2. So you are now in state 2, and then it says this pre-computed value for 2 comma naught, which is 0. This is because 2 is a terminal state and we already filled up all its returns. We set them to 0, so it's already set. Then it goes to 2 east, 2 west. Because it's in state 2, it will try to fill up all different actions corresponding to state 2, and everything is filled up to 0. Then it comes back. Now it tries 1 west 0. Now this is where it again gets into recursion, because from 0 you went to 1, then to 2, then you came back to 1. Earlier we had tried 1 east. Now it's trying 1 west. 1 west means, so this is cell 0, this is cell 1 or state 1, and you're trying to go west, which means you're going back to state 0, right? So from 0 you took east to 1, and then from 1 you're again taking west, and this time you end up in 0 again. And this will again cause problem because now you are going to look at 0 north, then 0 east, and 0 east will again take you back to state 1, right? So we are again running into indefinite recursion. This time it's not an immediate recursion, it's a cycle. So from state 0 to state 1, then back to state 0. But this is going to be a cycle because of the way the environment behaves.
How are you getting so much information? Mine crashes after like 2 steps. Mine like 0 north and then 0 east, and then it gives up.
Yeah. So do you have these debug statements in the right place? This debug statement should be placed before the recursive call. If you have this debug statement here.
Yeah, it is there.
It's the same for me.
So you don't see any textual output?
I only see the first two trying to fill, that's it.
And you're running it on Collab?
Yeah.
Do you mind sharing your screen? Because we had a similar issue, but that was because the debug statement was sort of placed after the else.
When you call a recursive function, did you pass in the debug argument?
Yes, I'm
Yes.
passing the debug. Yeah, that is also important. So are you passing the debug as it is?
Yes.
Okay, so I'll
Yeah,
stop.
should I share? Or
Yeah, if you can for a moment.
Did you put the else statement or not?
I'm back. All right. Okay.
so
This seems okay.
yeah, so I have the debug.
Right.
You're calling V0 instead of V1.
Oh, good point.
Yeah, that's
Yeah, I copy pasted the code from. All right. Now it's probably better. Okay, thanks. Cool.
Thank you. Yeah, so I'm going back to sharing my screen. Yep. So so if you have this exact code, then you should see the entire log, but you will have to spend some time understanding the log. I just tried explaining it, but again, we are running into recursion. Okay, and I think there's at least one more bug that is being reported in the chat, which is if you first populate a dictionary with zeros and nuns and then convert it to a data frame, the data frame perhaps converts the nuns into NAs. So yeah, that might be happening. And if you first just create.
Yeah, that was what I found, that I had to basically create first the data frame with all nuns, and then in the data frame replace with zeros. If I replace the zeros in the dictionary and then convert the dictionary to the data frame,
Yeah,
then
there might be some type conversion or data conversion going on. We'll have to see what it is, but yeah, seems like a bug. So so yeah, we are again stuck in recursion basically, and the question is how do we get out of this, because we have looked at dynamic programming problems for other dynamic programming solutions for other types of problems, and this does not happen often. This is happening in our specific case because the nature of the problem is such that, so when you're applying dynamic programming, you are visiting states, you are expanding states into other states, but because how this environment behaves, you can go from a state back to the original state. So if you think of it as expanding a tree, then it's not exactly a tree, it's a graph where you can have loops and you can go back to the same states. This is not the only problem where such loops arise, and so there is a way around these problems, and the solution happens to be iterative. So uh,
can you just
and
sort of save your path along with this, along with the max, and then if your state is in the path that you saved, you know that you have a loop, so you throw those out.
you can, yeah, you can try removing loops. You can try removing loops of length 1 or higher length. That is one way of doing this. um, but there is also an iterative option, an iterative solution which is used in problems like this one. There are some other interesting problems that probably I'll talk about in the next session, but these problems are quite natural. Wherever you have a system that behaves in this fashion, where you can come back to the original state, then you will inevitably have loops. And if you want to apply recursion or dynamic programming, then you have to learn to deal with those loops. One way of doing it is using an iterative method. So that is what you will see in the next cell. Because we are out of time, we are not going to attempt it to do today, we'll pick it up tomorrow. But I want everyone to spend some time, look at what that code is, like what the solution will look like. So the hints are here, right? So this cells talk about what changes could be made, so you don't have to deal with any of these recursions. We'll make those changes. It will be an iterative solution, and then tomorrow what we'll do is try to finish this so that we have returns in place, right? The whole idea behind building this table was that we will have return for every state and action pair, and then we will see that if you have those values of returns for every state and action pair, that's a very simple few lines of code to just figure out the best path from any starting position. So we'll see that tomorrow, and then obviously we'll write some more code, because what we essentially, if you go down and look at step 8 and beyond, so we'll talk about what policies are. Policy is basically what we have been chasing all this while. So policy is the solution to this problem. Policy tells you which action to take. So once you have the, what the returns look like for every state and action pair, then you want to formulate a policy, you want to derive a policy from this table, and the policy will tell you which path to follow. So we'll solve the original problem which we were chasing, which was finding the path with the best returns, right? So we'll look at policies, uh, but after that we'll talk a little bit about how to improve the policy. But we will see that after we do all of this, we'll get a policy, but it won't be a useful policy. It won't actually take you from the beginning to the goal post. So to do that, you will have to gradually improve the policy. So we'll see how to improve that as well, and that is again an iterative process that we will cover tomorrow.
So with respect to the dynamic program, what is the computational complexity order?
So yeah, so essentially it will be, because you are just going to fill that table, right? And you will sort of visit that once every cell will be visited. So it's typically rows into columns or states into action.
Okay.
Cool. If there are any questions, I can answer them now, or you can ask them in Slack. But we'll meet tomorrow and we'll continue from here.
Are we reviewing the? Sorry.
Yeah, please.
Someone else have it. Are we reviewing the iterative solution tomorrow, or should we do that on our own before tomorrow?
I would encourage everyone to take a look at it, think about how the iterative solution, because the hints are there. So just think about how it would work. But yeah, we'll actually work through it tomorrow.
Thank you.
Cool. I'm still here for some time, so if there are any questions, please ask. Otherwise, I don't want to hold anyone back. So
thanks.
Sure. Thank you.
Yep. Thanks, Farhan.
Thank you. Bye bye.